In this video, you will learn the holy grail of all collision detection algorithms. Why holy grail, you ask? That is because it can detect collisions for any type of polygon that you wish to use this algorithm on, under the single proviso that the polygons in question are concave and not convex. This means that although the demonstration you are currently seeing is just using squares, the algorithm in question is not limited to just basic shapes like squares or hexagons, for example. So long as the two concave shapes that we use the algorithm on to test for collision have both vertices and edges, they will be compatible for use with this algorithm. If you don't know what a polygon is, then it is just a shape that is made from both vertices and edges. Vertices are these points that structures the lines. These lines are referred to as edges. Therefore, cyclical objects like circles are not polygons. Curved edges cannot really be represented with straight lines, unless we had innumerable amounts of them, which would just be impractical. Because the Separating Axis Theorem deals with polygons, we are able to rotate the polygons and still have the algorithm work on these rotated objects. You can clearly see that this is the case in my demonstration. All it takes to do this is a bit of extra work, where we get the object's current canvas rotation, and then use trigonometry combined with Pythagoras' theorem on the original unrotated object's vertices, to construct a new polygon that represents the original polygon rotated, except that this polygon hasn't been rotated at all. It is a completely new polygon that has just been made. If this sounds confusing to you, then don't worry. We will touch up on this later on. To start though, we will just focus on the basics, what the theorem is and how it works. The theorem states that if we can draw a straight line that passes through the two polygons given to the algorithm, then we should never be able to find a gap in between the middle of the polygons. The line should be overlapping with a polygon right the way through as soon as it touches the first polygon until it comes out of the other polygon. This is the reason why the algorithm does not work with conclave polygons. In conclave polygons we can intersect a single polygon more than once, whereas in convex polygons we can't, and so the theory remains true. Obviously the practical application of this isn't as simple as the theory itself. For starters, we don't know the angle of the line that is meant to be passing through both of the polygons. There are just far too many different collision scenarios for us to know this information. What we will do instead is look at all of the edges of both polygons. Then we will get the vectors of these edges by working out the difference on both the x and y axis between both vertices that form the edge. Vertices and edges are listed in clockwise order, starting at the top right vertex first. Therefore, if you wanted to work out the vertex for edge 1, then you would subtract the respective x and y coordinates of v2, our starting vertex, from v1, leaving us with a vector that has a value of 0, minus 5. Once you have calculated these normal edge vectors, we are going to get vectors that run perpendicular to the ones that we have just calculated. This isn't hard to do. All we do is follow the standard rule of reversing the x and y values of the selected vertex, then negating the new x value, which essentially means just multiplying its value by minus 1, so that it will be a minus number if it was positive before, or a positive number now if it was minus before. Finally, we get the dot products of all our vertices against the newly calculated perpendicular vector. Dot products are used to project one vector onto another. We calculate it by multiplying our vertices x and y values by the matching x and y values of the perpendicular vector we are currently using. Then adding up these two numbers to finish with a single value, which is referred to as a scalar instead of a vector, which is two values. This will project our normal vectors onto our perpendicular vector. Although we do this for all vertices of a polygon, and therefore all edges, we only really worry about the two vertices that form the original vector in the first place. That is because they will hold the highest value dot product and the lowest value dot product between themselves. They will therefore help us detect a gap between polygons. The other ones won't, and so we will ignore them. These highest and lowest dot products from both polygons for a particular perpendicular vector will go into this inequality formula. All we need is either of these two statements to be met for the statement to return true overall. So in this case the statement will return true, but in this case it will return false. Now in this example the polygons are not actually colliding. Still though, in this scenario there is no gap between the highest and lowest dot products of the two polygons for this specific perpendicular vector. This is fine because the way that the algorithm works is that we only need to find one gap on one side for the algorithm to know that the two polygons are not colliding with each other. That is why as soon as we detect a gap, the algorithm will exit out of itself and return false, indicating that there has been no collision. The algorithm will only return true to signify that there has been a collision if the projection on every perpendicular vector for both polygons has been evaluated and not a single gap has been found. So here we have a work in progress version of the application that you saw at the start of the video. We've got the objects moving but have no way to detect for a collision. I will not be going over how to set up the project up to this point. Creating this requires some basic canvas knowledge. That is the purpose of other tutorials to teach, not this one. As for how we are getting the rectangles to rotate though. In the rectangle class, we have this current rotation field. It stores the current rotation of the square in degrees. It is set to 0 by default to mean that it's unrotated. When the user presses on the corresponding button, we will rotate the square by 1 degree in the correct direction on each frame that they are holding the button down. As for the code below, these two translate statements. The first one moves the canvas's origin, which is its top left corner, the centre of the rectangle that is currently being rotated. The second one moves the canvas origin back to what it was before once the rotation is finished. If we didn't do this, then the squares would be rotated in a way where their position would be moved out of alignment, due to it pivoting around a point that is way off from where the rectangle is actually located. As for this rotate method, all we are doing is rotating the canvas by the rotation field. The equation is there to convert the degrees that the field holds into radians, which is just another way of measuring angles that computers find easier to work with. Finally, we reset the current rotation back to 0 if the rectangle has been rotated a full 360 degrees in either direction, so that it will now be back to its original unrotated value. In the method that draws the current state of the rectangle to the canvas on every subsequent frame, we save the canvas's context just before it is rotated so that we can restore the canvas's context back to its unrotated state after the rectangle has been drawn to the canvas. This is to prevent the current rotation of the rectangle from interfering with the rotation of the other rectangle, as well as resetting the rotation of the current rectangle so that its rotational value is not continually added to the rectangle, making it rotate automatically without us wanting it to. We will also have this color field. We use it in the draw method to change the rectangle's color just before it is drawn to the canvas. Its value will be changed to red upon collision. Our application has two rectangles, both with the same width and height. They are created and held in this array. We loop through both of the rectangles in the array, then call the draw method so that both of them will be drawn to the canvas in turn. One problem with doing the rotation like this is that the data stored in memory, like the x and y offsets of the rectangles, are not reflective of the rectangle's current rotation. They represent the unrotated version of the rectangle, even if the rectangle currently being displayed on the screen is rotated. To solve this problem, we will pass in all of our vertices into this function. Its final argument is the current rotation of the square. This is because the function will return a value that represents the new vertice's position in relation to its rotation. So once we have used this function on all our polygon's vertices, we can construct a new polygon that represents the original polygon, rotated by the desired amount. So that's what the first four arguments mean. The center point of the square and the specific vertex that we want to translate based off of our rotational value. As for this rotational value, we convert it to radians because it will be passed into this function as degrees. The first thing that we will do is work out the horizontal and vertical difference between the square center point and the vertex that we are currently evaluating. With these values, we can use Pythagoras' theorem to calculate the distance between the center point of the square and the vertex. If you're wondering why we are using the center of the square, it is because that was our rotation's origin. We will also calculate the angle of this line that connects the center of the square with our vertex of choice. This atan2 function is the function that we will do this with. It returns an angle expressed in radians, and as you can see, it takes in the y coordinate first before the x coordinate. Finally, we will work out the new x and y coordinates of the original vertex by getting the relevant center coordinate and adding the distance to it, so that the vertex remains the same distance away from the rotation's origin as it was before. We then multiply its value by either the cosine or sine of the original angle, plus the rotated angle. Sine is used for the y coordinate because it is located opposite the hypotenuse. Cosine is used for the x coordinate because it is located adjacent to the hypotenuse. Essentially what we have here are two vectors, one for x and another for y. Remember that vectors have both magnitude and direction. The first part gives us the magnitude, where we add the distance to the center point. The latter part gives us the direction that will point to the vertice's new location. The function will return both of these values. Since both of our polygons are squares, we will create this function. It will construct a new square polygon based on the square that is passed into it and its rotational value. The previous function relied heavily on the square center point. We will therefore create it first. A square has 4 vertices. We will calculate their positions here. Finally, we will return the 4 vertices necessary to construct a square. They should now be in the correct position based on the square's rotational value that was passed into the function. This functional object will be a single vertex, which is why it holds both an x and a y value. This functional object will be an actual polygon. Polygons, remember, are made up of vertices and edges, which is why they have the fields that they do. Just so that you can see how this actually works, we won't be creating the Separating Axis Theorem just yet. Instead, we create this function. It will take an index of the square that is currently being looped through. We will get access to this square that is currently being looped through. There are only 2 rectangles in the array. Therefore, if the index is 0, then we know that the other rectangle will be stored at index 1 and vice versa. We will construct the rotated polygons for both squares. These 2 will now hold an object with 4 fields, each corresponding to the vertices that form a square. As mentioned before, edges and vertices are listed in clockwise order, starting at the top vertex first. This is why we list the top right vertex first here, using the vertex functional object that we created prior. The others then follow suit in the correct order. We then calculate the vectors for the edges, again in the correct order. Remember that when working out the distance between 2 points, we always subtract the end vertex by the start vertex. Again, we will need to do this for the other square, as we are checking for a collision between the 2 squares. Not too hard though. This is also a square, so we can copy the above code and just change TRR to ORR. With the edges and vertices for both squares calculated, we can pass in the relevant data into the polygon functional object to create polygons for both objects that will be given to our separate axis theorem function. So now we're actually going to create the separate axis theorem function. These are the variables that the function will be using. The last 4 relate to the minimum and maximum dot products for both polygons passed into the function. Remember the ones that will be used in the inequality formula. The only variable that will not be overwritten on a new loop cycle is this perpendicular stack array. That is because it will store all of the perpendicular vectors for both polygons. It does this so that it can be looped through and all of the projections can be made. This is simple enough. We loop through all of the edges of the first polygon, then calculate the perpendicular vectors of these edges and push them to the array that is meant to store them all. Of course, we will need to do the same thing for the other polygon. Once we have gotten all of the perpendicular vectors for both polygons, we will loop through them so that we can do all of the dot product projections. We are starting a new projection for a new perpendicular vector now. Therefore, the minimum and maximum dot product values need to start afresh. Here we are looping through all of the vertices stored in polygon A and calculating the dot products for them against the current perpendicular vector that we are looping through in the parent loop. At first, on a new perpendicular vector loop cycle, these minimum and maximum dot products for polygon A will be null. On the first dot products calculated, they will be assigned the first dot product value, so they won't be null anymore. As we continue through though and find new higher and lower dot products in polygon A, these new values will be assigned to the relevant variables to overwrite their previous value, so by the end of the loop we will have found the lowest and highest dot products. Again, we need to do the same thing for the second polygon. Obviously, this time we are using the min and max variables for polygon B instead of polygon A. Here is that inequality formula expressed in JavaScript code. If it is met, then we will use the continue jump statement to jump straight on to evaluating the next perpendicular vector, because we know that there is no gap between the 2 polygons. If there is a gap, then we will set the function to return false straight away. We no longer need to search through the other perpendicular vectors because we have found a gap in the dot product projections, and so the 2 objects cannot be colliding. If the loop ends though without ever returning false, then we know that there is a collision because we have never found one single gap in any of the projections. Therefore, we can return true to signify that a collision has taken place. So back in the detect rectangle collision function. So if this function returns true, then we will change the current rectangle to be red. Since this function will be called on loop, the other rectangle will also change color because they are both involved in the collision, not just one. Okay, and now I need to use this function in the loop. And as you can see, we've gotten access to the index of the current item that's being searched through in the array, so the function can actually work. And now we'll go on the application and see if it's working properly, give it some rotation, maybe some more. And as you can see, it's looking good. However, there is actually a problem, and that's, as you can see, if our squares are unrotated and we are meeting at exactly the same planes on either the x or y axis, then a collision is not detected. And you should be able to see it here. See, there's like a brief flash where it returns to black again because the collision is not detected. But this isn't really a problem though, because the Separating Axis Theorem isn't really designed to detect for collisions between unrotated squares. It's more for more complex polygons, and the way that we solve it is just through using the classic if one side is inside the other collision detection algorithm, which is the most basic out of them all, and it's only really applicable for rectangles. So we'll only do the algorithm if both rectangles are rotated, of course. And all of these conditions check to see if one side is further away from the opposite side of the same axis on the other square. If that is the case, then clearly there is no collision. This bang operator, which is represented by an exclamation mark, checks for this statement not being true. It also changes all these logical OR operators, as represented by double pipes, into logical AND operators. This means that if any sides collide with each other, then there is a collision, and we will change the rectangle's colour to represent this. So now we'll try this out one more time, and hopefully, yeah, as you can see, it's working. And then we scroll up, yeah, there's no collision there. And so this is it pretty much. I mean, I hope you understood what was going on here. I know that this was a pretty involved video with a lot of complex logic going on at the same time. So props to you if you understood it all. If not, don't worry, you are free to ask me for clarification anytime you want. Just post down in the comments box below, and I will be more than obliged to answer any of your requests. Anyway, that's all from me. Peace out and have a great day.